Okay, I'm going to first make a correction, and it was made last time at the end of the class, but it wasn't on the tape, so I'm going to do it on the tape. And so last time we were computing the cohomology of the Weil algebra. Okay. So let G be a Lie group with Lie algebra little g, and the Weil algebra is the exterior algebra on G dual tensor with the symmetric algebra on G dual. So if x1 to xn is a basis for G, and theta 1 to theta n is the dual basis for G dual in the exterior part, and U1 to UN is the basis for G dual in the symmetric part, then the Weil algebra is also the exterior algebra generated by the thetas tensor with the symmetric algebra, which is the polynomial algebra generated by the U's. Okay? And we have d theta k is uk minus 1/2 the sum of Cij theta I wedge theta j over Oj, and duk is the sum of Cijk ui theta j. Okay? So last time we called this zk. Then d theta k is zk, and dzk is 0 because it's dd. And then I defined an antiderivation k bar, okay, on the Weil algebra by defining it on the generator. So k bar of zk is theta k, and k bar of theta k, just a minute, so no, k bar of, yeah, that's right, yeah, zk has degree 2. So k bar reduces the degree by 1. And k bar of theta k, that should have degree 0, and it's 0. Okay? We defined that. And then we found that dk bar plus k bar d is the identity on the generators, theta k and zk. And now, because k bar is an antiderivation, v is an antiderivation, dk bar plus k bar v will be a derivation. Okay? So because it's a derivation, then when you apply it to products, you're going to pick up an extra constant. And then, so I defined k to be 1 over p plus q k bar on, okay? Now, lambda p generated by theta 1 to theta n, tensor with SQ. Okay, see, I think last time this is what I did, okay? But we have to use this new set of generators, Z1 to Zn. Then it's correct, okay? Yeah. Then dk plus kd will be the identity because now you have divided by p plus q on the direct sum of all of these, lambda p for p plus q greater than 0. Okay? So you can divide only if pq is not 0, 0. Okay? So this is the part of the Bay algebra with degree greater than 0. Okay? Yeah. No. Okay. Note that dk plus k bar is not a derivation anymore. So, yeah, k is not an antiderivation, but it doesn't matter. You don't need an antiderivation. You just need a linear map that satisfies this. Okay? And the degree of something in here, yeah, so if the alpha is in lambda p, say theta 1, theta n, tensor SQ, Z1, Zn, then the degree of alpha is, what's the degree of alpha if it's in here? Yeah, p plus 2q. Okay? Because the degree of the z's is 2. Yeah. Okay, and so then, because you have this dk plus kd is the identity, when the degree is positive, then the cohomology of the Bay algebra will be 0 in the positive degree. And then in degree 0, you only have r, the constants. Okay? So this is the cohomology of the Weil algebra. And yeah, I think this is the only mistake that I made last time. Okay? Instead of the generators Z1 to Zn, I use U1 to Un. Okay. Now, so last time I said the Weil algebra is an algebraic model for the universal bundle. And somebody asked me why. Okay, so I want to explain that a little bit. So, yeah. Why is the Weil algebra a good model for the total space of the classifying space? Okay. Well, the universal bundle it has the property that every principal G bundle can be pulled back from it. Okay? And it's more or less unique in the sense that any two universal bundles are G homotopic. So the base spaces are homotopic, and then the total spaces, they have an action of the group G. So they are homotopic via a homotopy, so that every time there is an action of the group G. So I'll just say that this is the unique, okay? It's unique up to G homotopy. G bundle such that for every principal bundle so there is a commutative diagram like this. You have a map to the classifying space, and then P is the pullback, and so there is a map this way. Okay? So the universal bundle has this property. It's essentially the only bundle that has this property for every principal G bundle. Okay? Now, the universal bundle, this is an infinite dimensional space, so it's not a manifold, but if it were a manifold, then you would have a de Rham complex. And the forms would pull back. So there would be a map like this. There would be a homomorphism for every principal bundle. Okay. Now, every principal bundle can be given a connection. And once there's a connection, then there's a homomorphism from the Weil algebra into the de Rham complex of P. So every principal G bundle P can be given a connection. Okay? This is something from differential geometry. And so there is a homomorphism from the Lie algebra into the de Rham complex. Where you map the theta k's to the connection forms omega k, and you map uk into the curvature form omega k. Well, we defined this last time, right? I call it the Lie map. Whenever you have a principal bundle with a connection, then there is this map, okay? And so you see, given any principal bundle, you have this map from the Lie algebra, okay? So it's like this. Given any principal bundle, there's a homomorphism from this into this. If this were a manifold, but this is not a manifold. And moreover, EG is contractible, so its cohomology is that of the point. And we have just shown that the Lie algebra has a cohomology of a point. Okay? Has the cohomology of a point. So it's in this sense the Lie algebra is an algebraic model for EG. Okay. Okay, so then last time I started trying to work out what the Lie model is for a circle action. Okay? So the Lie model is for a G space for a G manifold. M is well, you want a model for the homotopy quotient. Okay, so the homotopy quotient is obtained by first taking this product, and then you divide by G. Okay, and this is the homotopy quotient. So the algebraic model for the Cartesian product is the tensor product. So you take the tensor product of the Lie algebra and the de Rham complex of M. Okay? And then you want the forms on the base. So that's the basic elements of this algebra. Okay? So this is the Lie model. And it has an exterior derivative because each of these has a D. So the tensor product has a D. So this is the Lie model. Okay? And so an element is basic if and only if it satisfies two conditions, right? It's what are the two conditions for an element to be basic? To be basic means that it comes from the base. Yeah, it's horizontal and it's invariant. Okay? And if the group is connected, then it's invariant if and only if the v derivative is 0 with respect to all vertical vector fields. So, yeah. So let's we first worked out the, we first worked out the horizontal elements for a circle action. Okay. So for a circle action, the V group is S1. The V algebra is one-dimensional. Now, if you view S1 as the unit circle in the complex plane, then the identity is here. Okay. So the V algebra is the tangent space to the identity. So it's this vertical line. Okay, so it is the imaginary line. Yeah. The V algebra is I times R. Okay. There's an I there. Yeah. You know. Of course, this is isomorphic to R. And then, so we let X be a non-zero element in G. Then it's a basis of the Lie algebra. And so theta is the dual basis in G dual in the exterior part. And then we call U the dual basis, okay, for G dual in the symmetric part. Okay. And then the Weil algebra is lambda theta tensor with R of U. Okay. Now, lambda theta, in degree 0, it's R. Okay. In degree 1, it has only one basis element, theta. Okay. In degree 2, there's nothing, because this is exterior algebra. And we're taking the tensor product over R. Okay. And so this is R tensor R of U is R of U. So we get R of U. Okay? This is R again. So you get another R of U with basis element theta. Okay? So, yeah. Okay, so that's the Weil algebra. And then the Weil model is the Weil algebra tensor with omega m. So that's this tensor with omega m. Over R. So again, R tensor with omega m is omega m, so you get omega m u plus omega m u theta. Okay? Yeah, so an element of the Weil model is of the form A plus theta b, where A and B are polynomials in U with coefficients in the forms. Okay. And such an element is horizontal if and only if the interior multiplication with respect to all vertical vectors is 0, but you only need to use one vector because the Lie algebra is one-dimensional. Okay. And we worked this out last time. So when we worked it out, what we found was that this is equivalent to B is equal to minus IXA. Okay. Okay, so that says that the horizontal elements of the tensor product consists of all elements of the form A minus theta IXA, where A is a polynomial in U with coefficients in the forms. Okay, that's the horizontal elements. Okay. Okay, and now such an element is basic if it's invariant. So A minus theta IXA is basic if and only if, since the group here is connected as one, if and only if it's invariant. Is S1 invariant? And it's S1 invariant if and only if the Lie derivative is equal to 0. Okay? Okay, and so this implies that LXA, now, okay, this is equal to LXA, and then, what's LX theta? LX, let's work out LX theta, okay? So, now, Lx, by Carton's formula, is dIx plus IXD. So that's Lx. And what is Ix theta? 1, right? Because theta and x are dual. So d of 1 plus ix. What's d theta? D theta is u. It's, in general, it's u minus a half, a sum withCij's. But if you have an abelian group, theCij's are 0. Okay, so d theta is u. And d of 1 is 0. Ixu is 0, so this is 0. Okay? So Lx theta is 0. And Lx theta Ixa is, it's a derivation, so you first apply to theta, you get 0. Then you have theta Lxixa. Now, what's Lxix? See, this is Lx. If you put Ix at the end, this term goes out because Ix is 0. So you get Ixd. So Lx Ix is the same as Ixlx. Okay? Lx commutes with Ix. Okay? So you see, yeah. So if Lxa is 0, this term will be 0, and this term will be 0. Okay? So the condition for A minus theta Ixa to be basic is that Lxa is 0. Okay, so that just means that A is invariant. A is S1 invariant. Okay? Now, but A is a polynomial with coefficients in the forms. So A, you can write as well, it's a polynomial in the U's, right? So you can write it as say A0 plus A1U plus AK UK, where AI is a form on N. Now, yeah, let's see, what is Lx of U? Lx of U. Let's see. Again, this is dIx plus Ixd. And Ix of U is 0. And then d of U. U is d theta, so d of U is also 0. This is 0. Okay? So Lxu is 0. And and Lx is a derivation. So Lxa is 0 if and only if you apply Lx to this, you see you get Lxa0 plus Lxa1 u Lxak u to the k is 0. Right? And a polynomial is 0 if and only if all the coefficients are 0. Okay. And so what this says is that A is invariant under S1 if and only if all the coefficients are invariant under S1. AI are all invariant under S1. Okay? Let's write it like this. These are the S1 invariant forms on M. So finally, now we have a description of the basic elements in the Weil model. So WG for a circle action, WG tensor omega M and a G manifold. And the basic elements of WG tensor with omega M, it looks like this. It looks like A minus theta IXA, such that A is a polynomial in U with coefficients in the S1 invariant forms. Okay? And so there is an isomorphism from the Weil model to this space. The space of polynomials in U with coefficients in the S1 invariant forms, where you send A. Now this you can write as 1 minus theta IX A. Okay? So this you send to A. And then you can go backwards. Okay? Yeah. A goes to this. Okay. So this is a simpler description than the Weil model, and this is called the Carton model. Okay? And there's a differential here, D, okay, that we will call the Weil differential. And that differential will correspond to a differential here, which is called the Carton differential. Okay? So let's try to work out the Carton differential. Right. What should the Carton differential be? Okay. Now, the Carton differential it's the D that goes from the Carton model to itself. Okay. And we will denote it by dx, okay? Because it depends on the choice of x, an element of the Lie algebra. Everything here depends on the choice of x. Okay? Theta is dual to x. Okay? So, okay, so this map, okay, now there's an isomorphism with WG tensor with omega n basic. And then here you have the Weil differential D. Okay, so the Carton differential of an element A should be whatever you get over here, and then you come back by this isomorphism. Okay, so let's call this map lambda. And then when we come back, let's call it phi. Okay? So this is lambda, this is phi. Okay? So now this isomorphism, I think probably makes sense to call it the Weil-Carton isomorphism, okay? Because it's the isomorphism from the Weil model to the Carton model. So the Carton differential is the map in the Carton model that corresponds to the Weil differential under the Weil-Carton isomorphism. It's a linear map corresponding to the Weil differential D under the Weil-Carton isomorphism. Okay. So to compute it, you start with an element A in the Carton model, and then you want to compute dx of A. Okay, so first you should map it by lambda, then by D, then by phi. Okay. Lambda takes A to A minus theta IXA. Okay. And then D takes this to dA. Okay. And then d theta is U. Okay. D is an antiderivation, so if you move it across theta, you pick up a sign, and then you have d IXA. Okay. Now, what is Dixa? Now, Dix, it's Lx minus Ixd, right? By the Carton homotopy formula, Lxa is 0 because A is invariant. So this is minus Ixda. Okay, so here this becomes phi of dA minus Uixa plus theta, okay, minus theta Ix dA. Okay? And you see, what I would like to have is minus theta Ix, this guy again, dA minus Uixa. I like to have that because then I can calculate this map easily, right? Okay, so what is theta? What is Ix Uixa? If you work this term out. Zero, because Ix is an antiderivation, so it's Ixu, Ixa plus U, Ixa. Now Ixu is 0, and Ix is 0, so this is 0. So this extra term is 0, and so you can put it there. dA minus Uixa. Okay? And you see, so you have this minus theta Ix, the same thing again. Therefore, phi of it is dA minus Uixa. Okay? So that's the Carton differential. That's important enough that we should put it here. So the Carton differential dx is equal to d minus Ux. That's the formula for the Carton differential. Okay. And this with the Carton differential is the Carton complex or the Carton model. And so another way to say the Equivariant Ram theorem is that the equivariant cohomology under a circle action of a manifold is the cohomology of the Carton model. Okay? So this is another way to state the equivariant Ram theorem for circle action. And as I said, we are going to assume this for now and just use it to do some calculations. Okay? Okay. So let's take a break for 10 minutes. And then we'll come back and do some calculations.
Is it possible that this differential is independent of the choice of x?
Yes.
Okay.
Yeah,
It
this
is.
particular formula depends on the choice of x, but yeah, but you can you can define it so that it's
Use the dual
independent.
x,
Yeah. So yeah, right. Actually, here this formula is actually independent of the choice of x, because if you use a different x, it's going to be
multiple.
a multiple, say, c times x. But then the dual would be 1 over c. Yeah. So actually, this formula already is independent of the choice of x. Yeah.
当上 map will define 是光有正还是不容易看出？
这个 map so yeah, it's well defined because we already showed that all basic elements look like this. There is a term which is a polynomial in U, which it doesn't have theta in it, and this one has theta in it, right? So, I mean, an element here either has a theta in it or it doesn't have a theta. So, all you do is you drop the term with the theta. That's your A. So it's well defined. Yeah, once you pick that basis element, right? Yeah, but it is possible to, give a presentation that does not depend on the choice of a basis, but for doing calculations, it's better to pick a basis. Yeah. Okay.